Hey everyone, our project title is Experimental Modeling in Water Flooding. My name is Ahmed Zigel.
I'm Steven Maggio.
Coleman Watson.
Bradley Doucette, and we are Team 12.
I will start the presentation with the problem statement. First, the goal of this project is to build an inverted 5-span model for experimental testing. Next, this model will be used to confirm and help understand how varying mobility ratio affects the water flooding process. And finally, provide a functioning model for future petroleum students to use in the reservoir mechanics lab. I will give it to Steven. He will talk more about the project objectives.
So here I'm going to start with the project objectives. First, we built a light table. Coleman was in charge of the light table. The light table is what we are going to place our model on, and we will also have light shining through to see the advancement of the fluids through the model. Next, we will construct a sand pack. Bradley will be in charge of this. We will be injecting our fluids through the sand pack to test the different mobility ratios, and Bradley will discuss later on the slides how we're going to construct the sand pack. Ahmed and I are in charge of connecting the injection and production attachments. This includes phenolic blocks, tubing, and valves that we will be use to inject and produce the fluids. The tubing and the valves are 3/8 inch diameter, and this is to give us an optimal flow rate. Once our model is complete, we will begin troubleshooting and doing trial runs, and this is to test if our model is functional. And once the model is functional, we will begin running experiments. And I'm going to start talking about these experiments here. So the 3 experiments that we will be running is 3 different mobility ratios. We're going to have it equal to 1, less than 1, and greater than 1. To change the mobility ratio, we change which fluids will be injected and produced. We have 2 fluids that we will be using. We have Soltrol, which is placed here, and we also have naphtha. And these 2 fluids have different viscosities, which will give us the varying mobility ratios. As we are injecting these fluids, we will observe how the area is swept, and we will do this with the light table. So we will be tracing the fluid progressing through the sand pack. Once we have done this for each mobility ratio, we will compare the 3 experiments to see which mobility ratio will produce the greatest aerial sweep efficiency and therefore produce the most amount of fluid from the reservoir. Now I will hand over the results to Coleman.
So here we have some results, as Steven was saying. Our lighting table platform has already been assembled. We constructed the lighting table from scratch. We bought all the materials necessary to build this table from Lowe's, and we were able to come in under budget than what we allotted for. So that's always a good thing. So just a quick rundown of the table. Here in the first picture on the top left, we're going to have a 16-foot post. We cut 4 posts that are 3.5-foot posts out of the 16-foot post. In the top right picture, we bought a 4-foot by 8-foot piece of plywood. We cut it in half. We used half of it to build these braces for the post and the platform, and we used the other half as the tabletop. Here in the bottom left you can see we attached the tabletop, and next we cut a 16-inch by 16-inch hole in the direct middle of the plywood, and attached a piece of plexiglass, screwed in a piece of plexiglass on top, which is going to allow the light to shine through, therefore showing our model. And then some cosmetics we added just for good measure. We added some wheels so we could transport it easily, move it around, slide. We also sanded the entire thing down just to make it look good and easy to touch and not get a splinter or something like that. And our final product with the lights is shown right here. As you can see, the lights and the entire platform. And now I'm going to give it to Brad to discuss some more results.
This is the mold that we constructed to help us build our sand pack. We built the mold using leftover wood from our table. We cut the mold into a 16 by 16 square so that will fit directly over the plexiglass on our lighting table. We're going to be using wax paper to prevent to seal off the mold and to prevent any fluids from leaking. The sand pack will be built using water, sand, and epoxy. We've decided to use different ratios of water, sand, and epoxy to test, and we're going to build approximately 5 molds, so we can test the ability to flow of each mold, and then choose the mold with the permeability that we desire.
Okay, so here our discussion. Over the years, industry has gathered a lot of data about water flooding processes. It's been widely used for a while now, for many, many years in the oil and gas industry. So we're gonna run our 3 experiments. We're gonna confirm the data from the experiment with what is already known in the industry, and really, so that way we can get a good show the importance of understanding the water flooding process. Here's a schematic. It's got 3 of our important variables that we're going to really confirm that is known in the industry. It's going to be mobility ratio, area sweep efficiency, as a function of fractional flow. So if we look right here, we're going to have our mobility ratio. If we look at the graph, less than 1, going to be good mobility ratio to have. And we take a water cut, or fractional flow of 0.9, and it's going to give us an aerial sweep of 90% roughly. We don't usually see, if ever, 90% recovery in the field, but the schematic is done from mathematical testing, so that's why we're going to be able to see an area sweep efficiency of 1. So whenever we get done with our model testing, we're going to analyze our results, go in depth and really see if our matches this schematic and see why, if it is different, why it's different, and display those results in our final report to understand why we got different results than the industry knowledge that's already in place. So now I'm going to give it to Bradley for future work.
So this is the future work that will need to be completed in order to finish this project. The first thing we're going to need to do is to test the sand pack in order to get the permeability that we need. We would ideally like the permeability of our sand pack to be 1 to 3 Darcy in order for our experiment to be completed in a reasonable amount of time. Next, we will need to bring the phenolic blocks that we purchased to the LSU Mechanical Engineering Lab, where they will be able to cut the block into caps, which we will fit onto the corners of our model, and these caps will allow for isolated flow into our model. And then once the caps are connected, we'll be able to connect our tubing and shutoff valves to the model, and this will control the injection and production of our fluids. Finally, once everything in our model is assembled, we will be able to troubleshoot the model to fix any issues that may arise, such as leaked fluids. And once everything is functioning properly, we'll be able to begin running our water flooding experiments. And now I'm going to let Ahmed conclude our presentation with acknowledgements.
At this time, we would like to acknowledge a few people. Bikash, thanks for being our mentor and giving us a valuable insight for this model. Dr. Rao, thanks for referring us to Bikash and being our advisor. Dr. Maliva, thanks for motivating and guiding us. And finally, Frank Maggio, Stephen's grandfather, thanks for providing the power tools to build the table and the mold. Thanks.
Thanks.